We have spent quite some time looking at rational equations. Now, let's take that step forward and start looking at them as functions. Here we have f of x is equal to 1 over x, a rational function. So let's try and graph this right here and see what happens. So let's start putting in some inputs. So we know from last video, we cannot put 0 in the denominator. So let's put some points around 0 and maybe see what happens. So firstly, why don't we put in 1? I want to make it symmetrical, so I'm going to have 3 negative inputs, and then, 1, 2, 3, 1, 2, 3 positive inputs. So I want to have 1. So we have 1 over 1, which is just going to be 1. Then maybe let's try 2. That'll just be 1/2. And then 5. So that's just going to be 1 over 5. And let's just do the same. -1, -2, -5. This is just simple substitution. -1, -1 over 2, -1 over 5. Okay, so quadrant 1, that's our first point. Our second point at 2 is going to be at the halfway mark. And then 1, 2, 3, 4, 5. Our fifth point is going to be at 1 over 5. It's going to be extraordinarily close to 0. Now look at our negatives. I'm just going to kind of get these smaller for a sec. Our first point is just going to be at 1, 1, or -1, -1. At -2, it's going to be -1/2. And then again, at -5, it's going to be at -1 over 5. Well, let's try and connect these dots. And so we can look at this behavior and see that it gets extraordinarily close to 0, but because our outputs, they're only going to get bigger. But since this is a fraction, as our denominator gets bigger, our output gets smaller. That's why it doesn't quite touch it doesn't quite touch 0. It doesn't quite go past 0. It just approaches 0. That's why we can assume that it's going to keep going this way. Put the arrow, and put the arrow. Now, we can see this trend as it gets closer to the y-axis right here. It's going to increase. We can see that. But how does that going to look like? Here we can assume, but here what happens, we know that we cannot put 0 here. So let's put some rational inputs, some fractions between 1 and 0, and see what we get out. Okay. So from the positive side, let's put in 1 over 2. If we have 1 over 1 over 2, that's the same as 1 divided by 1 over 2. Flip it over. 1 times 2. So we put in a rational input. It's just going to flip it around. So 1 over 2, that's just going to be 2. 1 over 5, that's going to be 5. 1 over 10 is going to be 10. -1 over 2 is going to be -2. -1 over 5 is going to be -5. And then -1 over 10 is going to be -10. So at 1/2, it'll be right here. At 1/5, it's going to be all the way up here. And then at 1/10, it goes beyond what my graph even shows. Same here. At 1/2, it'll be at 2. At 1/5, it'll be at 5. And then at 1/10, it's going to go beyond what we have here. So, connecting these points, we can see that it does not even pass the y-axis at 0, because the x-plane tells us what our inputs can be, but this says that you cannot have 0 as an input. So that's why the behavior of the graph changes as it approaches 0. So we can say with almost certainty that a rational function will look like this. Quite an interesting looking graph, no? At this time in your Algebra 2 career, you've only seen, concaves and cubics, quartics, all those squiggly lines. But here, the first foray into an interesting looking function. But you see, there are some lines here that are not touched at all. You see, on our outputs, it can never touch 0, because as our inputs get larger, the fraction is only going to get smaller. We have put in a billion right here. It will be 1/1,000,000,000. It's going to be extraordinarily small, but it's not going to be 0. You can see as this graph gets greater and greater and greater, it's going to get smaller. And as our inputs get smaller and smaller and smaller, closer to 0, our outputs get extraordinarily large. There is a name for these invisible lines. They're called asymptotes. An asymptote is a line that is approached but never touched. Rational functions usually will have both a horizontal and a vertical asymptote. It's possible for them to not have them, but different video topic. But here there clearly is one. As we can see, it cannot touch 0 and it cannot cross 0. So how can we describe this? Well, we can say that we have a horizontal asymptote. Horizontally at y = 0. I know you can think of horizontal as, the x-plane, but when describing asymptotes, we describe them using at what point they cross their corresponding axis. So the horizontal will continue going this way, it crosses it at y = 0. So we have a horizontal asymptote at y = 0. Now we also have a vertical asymptote here. And I know you can think of vertical as our y-axis, but we are using the x-axis here to describe where the vertical asymptote touches. So our vertical asymptote is at x = 0. Now, to draw this out, usually my teacher did it like bullet lines. To show that these lines are the asymptotes. Now, a big part of rational functions, especially in homework, is describing them. As in, where are the asymptotes? Are there any domain restrictions? What is the end behavior? Spoiler for future video. Are there any holes? Spoiler for another future video. And here we clearly do have a domain restriction. Hint, your vertical asymptote is always going to be your domain restriction. or your range restriction. We can say that for our inputs, x cannot be equal to 0. We have to restrict our domain. We don't have to restrict our range because we can't control what our range is going to be, right? We can only control our inputs. That is why we restrict our inputs. What happens at y equals 0, or what happens at x equals 0, y equals 0, is not up to us. But we can choose to put in 0 and, break this. Rational functions. Pretty neat.